In this lecture, we will continue our discussion on normal shock waves, and we will also introduce Mach waves and oblique shock waves. In our previous lecture, we were discussing about the hypothetical state changes of a compressible flow, and thereby we came across the concept of characteristic Mach number m star and also a star when we either accelerate or decelerate a moving flow to a sonic condition. Additionally, we also talked about slowing down such a compressible flow isentropically to 0 velocity, and thereby we discussed about the stagnation conditions. Let us recall about the energy equation and try to look at it from a calorically perfect point of view. In that case, the energy equation will be written in this way. Remember that this is nothing but H at the station 1 and at the station 2 respectively, and note that the above form of energy equation is of course valid only for adiabatic flows, otherwise you have to include the heat transfer term. And then what we are going to do is will remove the subscripts for station 1 and imagine that the gas reaches a stagnation condition at station 2. All right. So, we are talking about slowing down the fluid particle from a state of motion to 0 velocity, and therefore, we will bring in the concept of isentropic slowdown in due course, but not immediately at this point. So, when it slows down to 0 velocity, we have the concept of stagnation temperature coming up. So, the static part gets absorbed into the dynamic part gets absorbed into the static part, and therefore, the static part gets elevated to the stagnation condition. Now, we need to take note of a very important point here, that when we are defining stagnation temperature T naught, the flow needs to be adiabatically slowed down. It does not necessarily need to be slowed down isentropically. This is a very important point, because the energy equation is based on an adiabatic assumption, nothing more. We are not saying that it has to be necessarily reversibly adiabatic. Therefore, just adiabatic condition is sufficient in order to bring in the concept of T naught. Once you have done that, you can evolve an expression for T naught by T, which is nothing but the ratio of stagnation temperature to static temperature. And then what you need to do is you divide this equation by Cp T, and then you can show finally it comes out to be 1 plus gamma minus 1 by 2 m square. Therefore, the stagnation temperature to static temperature ratio is given by this expression. So, higher the Mach number of the flow, higher would be the stagnation temperature with respect to the static temperature. Now, if the state 2 was reached by the gas through an isentropic process instead of just an adiabatic one, that means you are bringing in the concept of reversible adiabatic, then what can we do? We could use the following relation to connect the stagnation pressure and stagnation density with stagnation temperature. So, that is the additional connection you will be able to bring in. So, this is the isentropic condition connecting pressure, density and temperature ratios. Thereby, now you can say that if it is an isentropic deceleration, then the pressure ratio P naught by P will now be a function of m using this equation, or rho naught by rho, which is the stagnation density ratio, will again be a function like this. You need to take note of the differences in the indices here. Okay. So, this is stagnation pressure, this is stagnation density, and now you have a connection between the stagnation pressure ratio and density ratio with Mach number. Let us look at some more relations related to normal shock. So, we recall that the continuity, momentum and energy equations for the case of a normal shock placed inside a one dimensional control volume that we have already derived. We know that what are the fluxes which are balanced across a normal shock, and we had 5 equations to solve and 5 unknowns to be worked out from those equations algebraically. If you do that, you will be able to come up with the following equations which show you the change in Mach number or density or velocity or pressure, temperature, enthalpy, etc. So, it is only those 5 equations which have to be solved ultimately, but additionally if you bring in the concept of A star, M star in between, the derivations become simpler, and that is why we have already introduced these terms. So, you can try deriving these equations on your own later on as a homework problem, or try to refer to some of the references which I have already stated in earlier lectures in order to go through the detailed derivations of these equations, which we are stating directly without proof. So, you use this equation to find out the change in Mach number across the normal shock, and we are talking about the upstream state as 1, the downstream state as 2, and here is the normal shock standing in between the upstream and downstream locations 1 and 2. You will find that if you substitute a supersonic Mach number, that means any value m1 greater than 1 on the right hand side, and consider gamma is equal to 1.4, which works fine with air at standard conditions, then you will always find that m2 will turn out to be less than 1. It is not only less than m1, but it also turns out to be less than 1, which means a supersonic flow becomes subsonic on crossing a normal shock. Also remember that you do need a supersonic flow for a normal shock to exist. A normal shock can exist only under such conditions. It cannot exist in a subsonic condition, for example. In fact, below sonic condition, you will never see the existence of a shock. So, that is the learning from the Mach number equation. Of course, we end up ignoring the negative root from this equation. What about the density ratio or velocity ratio equation? You will find that the Mach number becoming less than 1 would indicate that u2 becomes less than u1. That means the velocity drops, and drops in what manner? It is an abrupt drop. Velocity was higher upstream of the shock. So, u1 was larger, u2 becomes abruptly smaller, and this is where the shock lies. There is almost a sudden jump in the velocity, a sudden reduction. What does density do? Density compensates. The density rises across the normal shock to compensate. Why? Because ultimately the product of density and velocity has to remain constant. That is what your steady continuity equation has conveyed. So, those will come out from an equation like this, where again you find that if you just substitute the upstream Mach number here on the right hand side of the equation, you will get those ratios. So, we have seen that m2 has been expressed as a function of m1. So, let us call the function as m. Similarly, rho 2 by rho 1 or u 2 by u 1 has been expressed by some other function, let us say d m 1, d for density. If you go to the next equation, which shows you the pressure ratio, you will find that if you substitute a value of m 1 greater than 1 over here, naturally this will give you a value which is positive, which when multiplied with this term, which is also positive, will give you a value greater than 1, which means the pressure beyond the normal shock is higher. That means the normal shock has created a compression in the flow. If the m 1 is larger, there could be significant compression of the flow produced by the shock. In fact, this is one of the mechanisms by which compression is produced in high speed flows, sometimes even with a purpose. Let us come to temperature or enthalpy ratio, that is static enthalpy ratio. These are equivalent in the case of calorically perfect gas, where your Cp is a constant essentially. So, here again you just need to have Mach number and your job is done. You just substitute it on the right hand side and you get the ratio. So, in the previous equation you had P 2 by P 1, that is the pressure ratio expressed as a function P m 1, and here maybe you can express temperature ratio as another function T m 1. So, you are just using the upstream Mach number on the right hand side of the equation to obtain these ratios. Again here you will find that T 2 will come out to be greater than T 1, which is rather easy to argue from the terms that you have on the right hand side of the equation. Finally, we are looking at entropy rise across the normal shock. We will find that this will turn out to be a positive term. So would this. If this turns out to be a positive term, then that basically means that P naught 2 is less than P 1, P naught 1, which means that there is a reduction in the stagnation pressure. Stagnation pressure reduces across a normal shock. Therefore, the rise in entropy also directly signifies a loss in stagnation pressure, which is a very, very important fact in compressible flows. Wherever there is a normal shock, there is going to be a rise in entropy, and rise in entropy also means that there is going to be a reduction in the stagnation pressure. This is a very, very important issue in jet engines which function at high speed conditions. So, we had some more on normal shock waves. Let us now get into a discussion on Mach waves. Let us talk about a very, very weak disturbance which is moving through a stagnant medium, a stagnant gas. What could be this weak disturbance? It may be just a beeper, a small source which is creating beeps, that means it is emitting sound waves. It is a really, really small source of disturbance, and let us say it is moving at a velocity v which is less than the sonic velocity. What happens is, after a while you will notice that it is emitting the sound which moves around it and forms circles, in the sense that you allow the sound to propagate to the neighborhood and it would propagate out with a velocity of a, and therefore, if you are tracking the sound over a certain time, for different instants of time the sound would have moved different distances. Let us try to mark them. So, let us say when you allow the time t 1, it has gone this distance. When you have allowed a time t 2, it has moved out the bigger distance here, and they are forming concentric circles. Here the sound source is static. Now, as we said earlier that you make the sound source to move. In that case, what happens is you will see that the disturbances are propagating out more like this. Okay. So, what has happened basically is that we have looked at the movement of the sound source over a certain period of time. It initially was here, and after the passage of time it has reached here, and in the meantime the sound waves have reached out far outside. So, the source of the disturbance have moved this distance, let us say v into t, and the sound waves have moved out a distance a into t. So, the disturbance patterns they show up like this. What happens if the velocity of the sound source, again we consider that it is moving from the right to the left, you can of course consider it the other way also, there is no harm. In that case, how will it propagate? So, how would the sound waves propagate and how would the source of the disturbance propagate? Let us try to draw them. Because the V is greater than A here, what is happening is the source of the disturbance started moving from here and it reached this point after the passage of time t. In the same time, the sound waves could manage to propagate by a distance of a t, which formed this circle. But you can see that the disturbance source has gone far beyond that circle. In the earlier case, the disturbance source was enveloped within the circles, but this time it has moved far ahead. In fact, the sound waves which have been propagated out all through during this time period have remained inside a certain region, and that region is bounded by these two straight lines. What are these straight lines all about? These straight lines form the Mach waves. So, physically what are we talking about? We are talking about a coalescence of weak disturbances into weak pressure waves. Which are slanted. Can you find out the slant angle? Yes, it is possible. Let us try to mark the slant angle. Let us say it is given by the angle mu. So, we will mark the angle. So, by definition, the sign of that angle will be A t by V t from trigonometry, which is A by V and which is inverse of the Mach number. Therefore, that angle, which we call as the Mach angle, is sine inverse 1 by m. So, this is how weak disturbances propagate into a medium when the source of the disturbance is moving at subsonic speeds and moving at supersonic speeds. The Mach waves form only when the disturbance source is propagating at supersonic conditions. Remember that it is a very weak disturbance source. What happens if it becomes a source of strong disturbance? In that case, let us say you look at a shape like this, which we say a slender wedge. Notice that it has a sharp tip and it also has a small included angle at the tip, which makes it slender, that means thin, narrow. And you could have two situations. One is that this body is moving into a quiescent medium, that means the air is stagnant, but the body is moving towards the left, and thereby there is a relative flow which the body sees as if it is approaching from the right to the left, or rather from the left to the right, I am sorry. The body moves from the right to the left, but the flow appears to be coming from left to the right, and let us say the flow is supersonic. So, what did we say? We said that the two situations are equivalent. One is that the air is stagnant and the body moves from right to left. In that case, if you are riding on the body, you will see the flow approaching at supersonic conditions from the left to the right, like we have indicated here. That is one situation. The other situation is you keep the body fixed and you create a supersonic flow over the body which moves from the left to the right. So, both the situations will create this identical relative velocity, and that is all that we are interested with. In fact, this concept of keeping the body fixed and creating a flow over it is what is used in the wind tunnel situation. While in real flight, it is the other way around, that the body is moving while the air around it is either stagnant or moving with very small velocity compared to the velocity of the body. Having said that, once the supersonic flow reaches this body, this is a much larger source of disturbance or perturbation compared to the beeper that we saw in the case of Mach waves. What happens? The collision of the molecules on the body as the flow approaches the body again create ripples of disturbances propagating away from the body surface, but they cannot move far upstream because they are traveling at sonic speed. The disturbances are traveling at sonic speed through the collisions of the molecules. Therefore, they do not make their way far upstream, they accumulate somewhere, and that accumulation leads to formation of an attached oblique shock. Remember that it is not a normal shock, because the obstruction is not flat and normal to the approaching flow. If it was normal to the approaching flow, you would have actually seen formation of a normal shock. But because the obstruction is tilted at an angle to the approaching flow, which is not 90 degrees, therefore, the shock also gets tilted. It is no longer 90 degrees, and that is why it is called as an oblique shock. Remember that this leads to a two-dimensional flow across the shock, no longer a one-dimensional flow. Moreover, for the same upstream Mach number, this is weaker than the corresponding normal shock. We mark this angle as theta and the other angle as beta. What do they mean? Theta is half wedge angle. It is half the complete wedge angle. So, which is 2 theta basically. What is beta? Beta is the oblique shock wave angle, often just referred as wave angle. The half wedge angle is also called as turning angle. When we look at inviscid flows, there is no viscous effect near the wall. We are talking about flow slipping over the wall, and then we can imagine that the same wedge which was there in the flow, in the middle of the flow, is kind of embedded here as a part of a tilted wall. And then what you see happening when a supersonic flow approaches this so called compression corner, the effect is going to be identical, like what you saw in the case of the wedge. If it is the same theta, for the same Mach number coming from upstream, you will have the same beta. So, the effects are identical in the case of inviscid flow, mind it. The moment you have a viscous flow, there will be a boundary layer formation here. And when the shock interacts with the boundary layer, there is a complex flow pattern produced, which we will discuss later. Let us try to sketch the oblique shock and try to understand what happens to the flow as it crosses the oblique shock. Let us say it is approaching from the left with a velocity of v1 with a Mach number m1, and once it crosses the oblique shock, it is travelling with velocity v2, say Mach number m2, and by the geometric aspects of the problem that we have defined, this is theta, this is beta. What we do is we resolve the velocities upstream and downstream of the shock into components. How do we decompose them into the components? You have to watch carefully. We are decomposing them into components which are normal and tangential to the oblique shock. So, this is your oblique shock, and you have decomposed V1 and V2 into normal and tangential components. We will name them as, let us say, U1 and W1. So, this is what? This is the normal component, this is the tangential component, because these are parallel. Okay. And you can similarly define the Mach number corresponding to these velocity components. So, normal Mach number, tangential Mach number, and so on. Similar things are done downstream. So, you have a U2, Mn2, and here you will have a W2 and M T2. Now, the idea would be that you create a control volume by following two streamlines. So, you follow two streamlines and form a control volume. By including the shock inside. Let us even name some of the let us name the faces of the control volume. All right, and then we try to figure out what happens to the conservation equations when we apply it to the control volume. Obviously, we have to use it in the integral form, because we are defining a finite control volume over which we have to apply the conservations. You will find that once you apply the continuity equation, the equation turns out to be like this. And from the geometry, you can easily figure out that A1 is equal to A2, and therefore, you basically get back the continuity equation that you got for a normal shock. So, what have you done? You have done it. You have applied the continuity equation in steady form for that particular control volume, and I am leaving it as a homework problem for you to figure out how that worked. When it goes to momentum equation, you actually have to look at the tangential component and the normal component separately. You will not be able to get all of it in one go. It is similar to using x, y, z separate components of momentum equation, which we have seen earlier. You would be able to show that W1 is equal to W2. That means, the tangential component of the velocity remains unaltered. And what does the normal component say? It gives you an outcome identical to normal shock. That means, P plus rho u square remains conserved. When you apply energy equation, what do you get? You would get the same outcome that you got for normal shock. So, there are lot of similarities that you are seeing in the case of oblique shock, but there are also differences which we will see in the later lecture. So, one relation that we need to keep in mind for a normal shock is what is shown over here. It is called as a Hugonot condition or Hugonot equation. So, we said that normal shock is basically a compressive effect in a flow, and Hugonot equation shows that the internal energy increase across a shock is equal to the average pressure across the shock times the reduction in specific volume. So, this is the internal energy increase across a normal shock, this is the average pressure across the shock, this is the reduction in specific volume because the density is increasing. So, this is what is applicable for a normal shock. Try to explore whether this will also work for oblique shock or not. So, what did we study in this lecture? We discussed more about hypothetical state changes of a compressible medium. So, there is a spelling mistake, let me rectify that. We discussed about changes across a normal shock. Further, we discussed about formation of Mach waves, which are weak oblique pressure waves, and we also started discussing about oblique shocks, which are formed when oblique pressure waves becomes strong. Thank you.